Hi, I'm Jeff Clarkson. In May of 2023, I was asked to lead a project team to develop a new part on assessment of fiber reinforced polymer, or FRP, equipment for API 579. In April of 2024, I provided a live online seminar to members of the API 579 Fitness for Service Committee to provide education on FRP. The session covered material on design using FRP, damage mechanisms experienced by in-service equipment, detection of damage, an overview of repairs and monitoring, and the contents planned for a part in API 579 for fitness for service of FRP. The live session is being recorded here to be available as an ongoing resource for the API 579 committee. Since the initial session, some questions have been raised that provided opportunity to add some additional explanation. As well, there have been some updates to documents that were used in the previous presentation, and they've been updated here as well. This video is the fourth of 4 videos. This video is video 4. The previous videos were an introduction to FRP, FRP damage mechanisms, NDE to detect FRP damage. Now we're going to discuss 2 parts, remediation, mitigation, and monitoring, and the FRP part for API 579-1, ASME FFS-1. First, we'll discuss remediation, mitigation, and monitoring. The key items of this session are that several remediation methods have been in use for many years, and for the design process, construction code approaches can be used. The purpose of remediation is to restore fitness for service or extend remaining life, or repair a condition that's likely to lead to a problem and address expected future damage. Really, the initial thing that we'll start with is something that would actually result in a not fit for service conclusion, and that's a crack-like flaw, especially with unknown depth, possibly with leaks. Repairing these follows some simple rules, but the first one is welding is not possible. This comes from the first video, in fact, talking about construction methods and material properties. Application of new FRP layers with the required structural properties can be made onto the existing substrate. The design should also consider bending moments that are created by a change in the line of action of the stresses. This can use the design principles provided in codes like ASME RTP1, Boiler and Pressure Vessel Code Section 10, ASME PCC-2, that's Post-Construction Code -2, and ASME NM.2. Regarding material properties, the properties of the existing FRP materials have to be incorporated in the remediation design, because if the FRP materials that exist have suffered some damage, and they inevitably have, then that damaged state needs to be incorporated. And recognize and remember that damage to FRP will change the properties of the material. You can use RFM and knowledge of the reinforcement sequence if it's available. Now, when you add new material, it actually may use properties that are allowed by the standard used in the design. For example, and we talked about this in video 1, some standards have got some standardized constructions and some allowable properties that may be used in design. Those standards would be RTP1 and NM.2, where the properties come from NM.3.3, And as well, if you're using European code, EN13121 also has properties that are allowed for design. Common types of remediation involve a few things. One, for example, is structural reinforcement. This is done to repair cracks like the one I showed earlier. You can repair local reduction in RFM from bending moments in different locations, and that actually is one of the things that's being done by the worker in this, where these nozzles were applying bending moments to a shell that was causing cracking, and so he's in the process of adding reinforcement layers onto the outer surface to build the thickness and therefore support bending stresses better. You can install external ribs for external pressure stiffening, and you could install pressure boundary reinforcements at bending loads, which is again what the worker is doing in this photograph. It's usually applied as an overlay. Very little material was removed from here to do this. In fact, there was some surface preparation and new material is being added on top. Another example is to apply a replacement or additional layers on the process side to supplement the original corrosion-resistant layers. This may extend asset life by reducing damage from contents and process fluid. There are some considerations for this, not least of which is that we've seen many circumstances where these applications on the inner surface have not bonded well or been bonded well to the inner surface, so you end up with a bit of a false layer. Monitoring of equipment on an ongoing basis applies to in-service equipment to allow early detection of developing damage, remembering that this equipment is not static. Even if static loads and static chemical conditions are applied, the material is constantly changing as a consequence of its nonlinear viscoelastic behavior. Some process conditions actually require more frequent monitoring, depending upon the chemical environment and so on. Remediation and mitigation should be monitored regularly to establish the parameters for new remaining life calculation. So every time you make a repair or make a change, modify some equipment, you should monitor that regularly so that you can understand how it's now changing or how it has changed the behavior and performance of the equipment. As a continuing example, continuing with the scrubber from all of the previous videos, in this scrubber, which is exposed to an external pressure as its highest load condition, the owner wants a life extension for the equipment. That life extension needs to address the risk of elastic instability or buckling from external pressure applied across this zone of the equipment. You've got a combination of external pressure here and compression from the load of packing and other equipment attached to the shell above the sump area. To achieve this life extension, we found that adding a stiffening rib or increasing the thickness in this zone can extend the life by several years. This can actually be done on the outer surface of the equipment and could be done while it's in service. Unfortunately, I don't have a photograph showing what was done. What was done is that a stiffening rib was added in this region. So there was a circumferential stiffening rib added, and that significantly increased the stiffness and reduced the risk of elastic instability. Now we'll talk about the part to be proposed for API 579. Generally, for the part, any combination of stress, strain, chemical exposure, temperature, corrosion, or erosion will be applicable to this fitness for service assessment. The part evaluates nonlinear viscoelastic damage to the polymer. This includes cracks. It applies to FRP components that were built in compliance with accepted codes. It also allows for components that were not built in compliance with accepted codes. The flowchart for the part is shown here, and one of the things that we've done, we've added a little bit, is we've made sure that equipment is aligned with a construction code in this zone. So we basically obtain operational and maintenance history. We have equipment design and construction data put together in such a way that we can rate this against a construction code for design. Then we basically proceed as in most of the other parts. Does the component meet level 1 criteria? If no, can we re-rate it? And of course, if we can re-rate it, then we can we'll do that down in here. If we can't re-rate it or we choose not to, we can look at performing a level 2 assessment and so forth. The inspection data that's required is we need external observations for cracks or leaks and compliance with the construction code. We need details of actual pressures and pressure controls. To be honest, there's a lot of FRP equipment out there that was designed to a standard that does not allow for an internal pressure, for example, and then internal pressure is applied as a consequence of the operational setup or the installation by the owner. This equipment experiences, well, premature failure, and there are ways this assessment needs to be able to address that. We need non-destructive evaluation data that allows fitness for service assessment, and that includes ultrasonic thickness and any of acoustic emission results, acousto-ultrasonic data, or attenuation-based ultrasonic data. This also allows the use of cutout coupons where they're considered necessary. A level 1 assessment, fairly straightforward to determine if it's fit for service. There can be no leaks and no cracks. These are cracks with a detectable width. So if a crack is less than about 0.25 millimeters or 10,000ths of an inch, we really would consider it to be not detectable. If you can't get a knife blade into it, for example, then the crack isn't to be worried about at this point. The operating factor of safety can be determined, and that allows us to work this against the acceptance criteria that were listed for non-destructive evaluation and for damage, for the damage mechanisms. And then the acceptance criteria are listed here. This is directly from a table in the part, where we have specific criteria for leaks, cracks, operating pressures, and the non-destructive evaluation methods. For a level 2 assessment, if components are classed as not fit for service by visual inspections or acoustic emissions, this could use criteria for acousto-ultrasonic or attenuation-based ultrasound or cutouts from level 1. But at level 2, we also have we haven't changed the requirement for leaks, The cracks, we're actually determining if we can determine the crack depths and we're happy with that, the inspector is clearly happy with that, and we agree with the inspector, then that if they have determinate depth and we can compensate for that or account for it, then we're okay. The actual operating pressures are available, and we have possibility to look at non-destructive evaluation or stress analysis for the final part, and that is either acousto-ultrasonics or attenuation-based ultrasound only can be used, at which point we determine what the RFM of the structural layers is. Or for the stress analysis, we need to make sure that the strain at failure, the maximum strain at failure in the remaining structural component is less than the limiting stress or the limiting strain from the result for RFM and strain reduction. As well, for elastic instability, we're actually applying a criterion where you have to have a factor of safety essentially of 2 on elastic instability if collapse is an issue. For level 2 assessment, if components don't meet level 1 criteria, we take a look, we separate out the undamaged or the least damaged portion of the FRP, the zone, as we've discussed in earlier presentations or videos. And we look at what this lower limit of strain and say, is the RFM of the least damaged zone, let's say it's 80%, is the strain in that zone when it's treated as in isolation with participation by any of the other zones, is that less than this retained or the actual expected failure strain for the polymer as a consequence. So in fact, in this case, if we have 80% RFM in that structural zone or in that remaining zone, it means that we're reduced to about 35% of the original strain at failure, which means that if you've got a 3% strain at failure, you're down to about 1% of 1% strain, and so is the strain in that structural area less than 1%. Strain at failure given here is the percent of the original times the value from the resin or the polymer manufacturer or supplier. For level 3 assessment, that's again for something that fails at level 2, but we may be able to continue use. One application of that is if we have data that indicates that the actual change in failure strain for the polymer for the conditions that the equipment is operating under is different than the curve from the previous slide. So here it shows that the retained strain is much higher than than it was for the previous chart. And in that case, as long as you have good, reliable data that tells you that you can count on this, you could use this, for example, in your assessment. The other part is, of course, talking about remaining life. We know that the shape of change of RFM is like this green chart, and in fact, it will follow this basic formula. And at this point, we can easily come up with a remaining life according to this formula. So we can predict what the remaining life is to this end-of-life criteria. And here we've identified it as 40%, which is consistent for equipment with a factor of safety of 5 for external pressure and 6 for tensile. The contents of the part in the main body, we have assessment procedures and criteria, remaining life calculation, and discussion of remediation procedures. And in the annexes, we actually have quite a few because this material is quite new and is somewhat different than for metal alloys. We have the technical basis. We have calculations to determine alignment with codes. That way we're able to identify whether equipment as it sits is aligned with an existing construction code. Glossary, of course. Description of how to use classical lamination analysis for FRP Young's modulus. Annex for the use of ASTM C1332 to provide inspection data using attenuation-based ultrasound, and a proportionality, the annex describing how to construct the proportionality curves for acousto-ultrasonics and attenuation-based ultrasonics, and that proportionality curve is discussed in video 3, where we discuss how to put those together for those two methods. Historically, versions of this approach have been used globally for more than 15 years. And very high reliability has been achieved on more than 4,000 assessments. In fact, at this point, at this production, there are 0 failures that were not predicted. This is the end of video 4. This is probably the shortest of the group, and I invite you to provide any questions, ask any questions, give any feedback that you want to me as listed here with these coordinates, and I thank you for your time.